Hello and welcome. For our project, we decided to do transient equations and using that in something we both love to do, which is cooking food. Um, for our equation, or for our project, we decided to try and model and use transient equations to see how long it would take to cook a piece of meat. And so our problem that we're trying to solve is, say we had a barbecue later in the day, and we were in charge of cooking the meat, and we just wanted to calculate how long the meat would take to cook. That way we know what time we needed to start cooking the meat, so that way it is ready to be ready and fresh and hot when the barbecue is ready. There's not a lot of equations, anything that we can find online. It's just all by experiment and just a lot of what people have found out using, cooking it themselves and finding out for themselves. So when you are smoking a piece of meat, something that is called a stall happens where um, water begins to boil and it starts to cool the meat, and it doesn't the center line of the meat doesn't increase any longer. As you can see here in the middle, the center line of the meat stays at a constant temperature where the water boils and it's evaporative cooling. So we're going to model our problem in two different parts, one with transient convection and one with the stall, where the water is being boiled from the meat and leaving the meat. First thing we needed to do for our experiment was to calculate the heat transfer coefficient. We did this by first calculating the Grashof number, and then calculating our Rayleigh number, and then we were able to calculate our new correlation number, and also then calculating our BO number. And our BO number was greater than 0.1, so it is a one-term equation. So we use the one-term equations.
In order to calculate the total cook time of the meat, we split our model into two parts. The first part covered the cook time when the stall was not occurring. By knowing our Biot number, we could find our C1 and our zeta 1 values off the table, and then solve for our Fourier number. And once we had our Fourier number, we could easily solve for the time it took for that portion of the cook to be completed. For the stall, we had to be a little more creative, but in the end we just used a energy balance equation where E energy in equals the energy stored. The energy in was from convection, and the storage term was based off of a phase change. Rearranging the equation, we could solve for the change in time that would take for a volume of water or a mass of water to change from a solid or from a fluid to a gas.
So with the meat that we purchased and cooked, we took some measurements before, and we were able to use those in our equations and calculate the cook time without the stall. So the transient convection portion would be 7.79 hours, and the stall time would be 7.9 hours. When you add these two together, you'd get a cook time of roughly 15 hours. So for the experiment, we bought a pork loin and we cut it in two because it was the most cylindrical piece of meat that we could find. We also used some butcher's twine to shape the pork to be even closer to a cylinder throughout the entire cooking process. We weighed each piece of meat with a kitchen scale in kilograms and measured the average diameter and the length of each piece so that we could have the information required for our equations. To measure the temperature of the meat during the cook time, we used a Wi-Fi enabled grilling thermometer, which is able to measure the temperature throughout the cook time, and it records the temperature every 4 seconds of each probe. We had one probe in the ambient temperature of the grill and one probe down the center line of each pork specimen, as well as one on the surface of the pork. And after the cook, we were able to export all these temperatures to an Excel file so we could better analyze the information that it collected. So in our experiment, the total cook time ended up being 12.5 hours, which before, if you remember, our calculated cook time was around 15 hours. And while reflecting back on this, we weren't too disappointed. What we assume went wrong with our calculations was that with the stall. It's really hard to determine when exactly the evaporative cooling starts and ends, and we believe that it starts sooner than we think and overlaps partially with the transient conduction portions of our model. And because of this, because of the overlapping sections, our cook time ended up being slightly shorter than what we calculated.